So if that is the beginning, if there was no time before that, then I don't know how to explain the fact that it was so special.
What exists beyond the boundaries of our observable universe? Could a vast multiverse containing our universe as just one of many be the reality? Some cosmologists argue that the multiverse isn't just an intriguing concept, but a tangible reality supported by recent scientific evidence. Even renowned astrophysicist Neil deGrasse Tyson has joined this line of thought, acknowledging the existence of multiverses, although he acknowledges that the human mind struggles to grasp this concept. But what empirical evidence underpins the multiverse theory? If multiple parallel universes do exist, could we ever traverse between them? Is it conceivable to encounter alternate versions of ourselves? And why does Neil deGrasse Tyson assert that, despite the evidence, our minds find it challenging to comprehend the idea of the multiverse? Let's find out. The enormity of our universe is nearly incomprehensible. It encompasses hundreds of billions, perhaps even trillions of galaxies, each hosting billions or trillions of stars. Some cosmologists speculate that the universe might have a diameter of around 7 billion light-years, while others argue it could very well be infinite. But does the cosmos end here? The notion of parallel universes, a favourite in science fiction, implies that we might be living one of countless potential lives. However, the concept of multiverses extends beyond the realms of Star Trek, Spider-Man, and Doctor Who. Genuine scientific theories delve into and, in certain circumstances, lend credence to the idea of universes existing outside, alongside, or distant from, yet potentially resembling our own. The idea of a multiverse is rooted in concepts from inflation theory, string theory, and quantum mechanics. Our universe is widely believed to have originated from the Big Bang, a theory proposed in 1931 and supported by substantial evidence discovered over the years. However, certain aspects of the Big Bang couldn't be explained until inflation theory emerged in the 1980s. Inflation theory sheds light on what transpired in the brief moments just before the Big Bang. More than 13.8 billion years ago, the entire cosmos existed as a minuscule subatomic point. Then, this tiny point underwent a rapid expansion, surpassing the speed of light in all directions. As inflation gradually decelerated, it ushered in a surge of matter and radiation, giving rise to the fiery event known as the Big Bang. This explosion eventually led to the formation of atoms, molecules, stars, and galaxies, all held together by the force of gravity. During the period of cosmic inflation, the universe brimmed with energy that was intrinsic to space itself. This enabled the universe to undergo an exponential expansion, with more distant regions moving away at increasingly higher speeds. This theory aligns with our observations of the observable universe. The end of inflation is set in motion by quantum processes that unfold at various times and places. The regions where inflation ceases are believed to detach, forming bubble universes. These bubble universes experience their own Big Bang scenarios and can give rise to universes similar to ours or entirely distinct ones with different particles and physical laws. All bubble universes, including our own, continue to expand and are assumed to be isolated from other bubble universes due to the continuing process of inflation. As a result, interactions or collisions between bubble universes are improbable, and inflation might still be ongoing in some corners of the multiverse. Parallel universe theories also draw upon string theory, which is currently one of the leading approaches to reconcile the mathematical inconsistencies arising when we attempt to blend Albert Einstein's theory of relativity, explaining phenomena on a cosmic scale, with quantum mechanics, explaining events on an atomic and subatomic level. String theory aims to describe the entire universe, encompassing subatomic particles, the principles of velocity and gravity through the concept of tiny vibrating strings that exist in 10 or 11 dimensions. One intriguing aspect of string theory is that it permits various bubble universes to possess drastically different physical characteristics, including distinct forms of matter and divergent physical laws. When combined with inflation theory, which allows for an extensive number of bubble universes, this framework offers a plausible explanation for why our universe is incredibly well suited for the existence of life. In essence, it proposes that we are fortunate to be in the right universe among an almost infinite array of potential universes. Now let's turn back the clock and revisit Dublin in 1952, where Erwin Schrödinger delivered a lecture that carried a somewhat perplexing message. He cautioned his audience that what he was about to propose might sound outlandish. Schrödinger stated that when his equations seemed to depict multiple distinct histories, these were not mere alternatives, but rather they all unfolded simultaneously. This notion of coexisting possibilities is known as superposition, and it's a concept that can be quite challenging to grasp. Neil deGrasse Tyson once remarked that our brains haven't evolved to naturally comprehend quantum mechanics and the vastness of cosmic phenomena. Tyson added that in the context of the multiverse, there could be regions within the universe expanding without any awareness of other such regions. These would essentially be independent universes, never intersecting with one another. He drew an analogy, likening it to ships at sea. Each ship represents an independent universe with its own horizon, and they remain oblivious to one another's existence unless by some mysterious means their horizons overlap. In our universe, we don't know how to achieve this overlap because these universes are non-causal, meaning they don't affect each other through cause and effect. To traverse from one universe to another, you'd have to find a way to tunnel between them, which could be perilous. If the laws of physics in another universe differ from those you evolved with, it could result in catastrophic consequences, like your biological chemistry breaking down due to changes in the fundamental properties of particles. Tyson also explained that the laws of physics as we know them were established during the universe's earliest stages. Quantum fluctuations could be responsible for another universe having slightly different laws of physics. These fluctuations can set a universe on a divergent path in terms of its physical laws compared to our own universe. This process could continue indefinitely, producing a multitude of universes with varying laws of physics. Nevertheless, some physicists are not entirely convinced about the legitimacy of the multiverse as a subject of scientific inquiry. They've raised concerns that the pursuit of the multiverse, without the possibility of experimental verification, might undermine public trust in science and have detrimental consequences for the study of fundamental physics. They argue that the multiverse should be classified as a philosophical concept rather than a scientific hypothesis, because it can't be empirically proven or disproven. The ability to test a theory through scientific experiments has long been a fundamental component of the scientific method. Renowned Nobel laureate Steven Weinberg expressed that if the multiverse were indeed real, the prospect of finding a rational explanation for the precise values of fundamental constants, such as quark masses, within our observable universe would be futile. Instead, these values would be a product of chance, determined by the specific region within the universe that we inhabit. Recently, a group of scientists delved into data obtained from the Wilkinson Microwave Anisotropy Probe, an unmanned spacecraft operational from 2001 to 2010. This probe measured temperature discrepancies across the celestial sphere within the cosmic microwave background, the radiant energy left over from the Big Bang. Their analysis seemed to imply that our universe might have experienced collisions with other parallel universes in the ancient past. Nonetheless, a more comprehensive examination of data gathered from the Wilkinson Microwave Anisotropy Probe and the Planck satellite, a space observatory managed by the European Space Agency from 2009 to 2013, which meticulously charted the irregularities within the cosmic microwave background, didn't reveal any statistically substantial proof of universe collisions. There was no discernible gravitational influence from other universes acting upon our own. To make things less favourable for proponents of the multiverse hypothesis, it's worth noting that the Planck satellite boasts 3 times the resolution of the WMAP, making its data even more precise. Despite this, some well-known scientists, including Max Tegmark and Brian Greene, have formulated classification systems for the various theoretical types of multiverses and universes that might exist. Max Tegmark, for instance, has outlined 4 levels of universes beyond our observable universe. Level 1. This level of parallel universe presupposes that space is infinite and the laws of physics remain constant. Within this infinite space, there exist other planets, solar systems, and even galaxies akin to ours. This is based on the idea that there is only a finite number of ways fundamental building blocks can arrange themselves. Our universe is defined as what we can currently observe, while any parallel universes would statistically be far removed. This concept aligns with many scientific observations and well-supported theories pointing towards a vastly expansive, possibly truly infinite universe. Level 2. In this type of parallel universe, there may be regions where the fundamental laws of physics are the same, but there are variations in physical constants, particles, and even the number of dimensions. These universes would be generated when cosmic inflation produces different bubble universes. Level 3. Level 3 multiverses are frequently depicted in popular culture. They arise from small or large changes based on the many worlds interpretation of quantum mechanics. This interpretation posits that for every conceivable quantum possibility, there is a universe where that possibility is realized. For instance, one universe where you stop to pet a dog and another where you don't. Level 4. This is the most extreme type of parallel universe, where other universes follow entirely different physical laws and are described by wholly distinct mathematical equations. It combines the bubble universes predicted by inflation theory with the vast variability allowed by string theory. Tegmark suggests that this level completes the hierarchy of multiverses, and there isn't a level 5. Enough head scratching for today. Do you believe in parallel universes? Share your thoughts in the comments below. Also, please show your support by liking, subscribing, and ringing the bell to never miss videos like this. Thanks for tuning in.